the person taking a test would look at this and say, okay, what do I have? I got a sample of 45 student drivers, n equals 45. The mean, 5.7 minutes. But that's a sample mean. So that's going to be x bar is equal to 5.7 minutes. With a standard deviation of 2.1 minutes. So S equals 2.1. Don't lose sight of the fact that with statistics, our goal is to take information about small samples and project out to the population. All right? So I kind of look at it like kind of like a floodlight, the old bat signal. I can't draw a bat signal, I don't think. You see, I already screwed it up. I tripped at the finish line. But anyway, you have a little light here. Maybe like a little tripod kind of thing. Actually, I'm going to make that light smaller. Make it like a single point. Yeah. All right, so you have your sample and you have your population. Information about your sample projects out to become information about the population. All right, so what is true for the sample would then necessarily, if the sample is representative of the population, would then be true for the population. You know, you just think of characteristics. You know, like not a kaleidoscope, but those little, what you call it things, the kids' toys, where you have the light and the little film thingies that you put in it, and then it's like the wheels, and you turn the wheel and it projects onto the wall. The level of detail within the individual film relates to the level of detail in the product on the projection. Right? That's the idea. So if you have more accuracy in your sample, then you're going to have more accuracy in your population. There is a relationship. It's a function relationship. All right? So that's the idea. So we're going to have information in every case about a sample. I'll take as a typo. I would like to have some bat signal, like official, like artwork in there. Because that look at that. People look at that and be like, what the hell? That's not, that's it. I don't even know what it is. Yeah, it's bat garbage. Bat droppings. So, guano. Alpha is 0.01. Guano bulls. Collect the entire set. So, 0.01 significance level test to claim that the mean time it takes for students in general to go through the routine is greater than 5 minutes. Greater than 5 minutes. Mean time in general. Mean in general. That's the same as saying the population mean. Specifically mu. All right, so that would be the mean or the average for all. All would be a population. And we want that to be more than 5. It's got a greater than symbol in it, which means it does not have an equal sign in it, which means it can't be a null, it has to be an alternative hypothesis. The corresponding null hypothesis would have all the same ingredients, just with an equal sign. I mean, if you know the particular hypothesis test, the hard work is over. I mean, the challenge is knowing that it's got to be a t-test because, again, once you get the hang of, all right, do I use a mu here or do I use a p? What information is in the problem that's relevant? Things like that. Then it's a matter of getting to the right test. So stat test 2. This menu is a little bit more complicated, but not alarmingly so. At least, let's put it this way. The first time you look at this menu is the day of a test. Okay, you're going to be alarmed. But if you're with me now and you're focused, paying attention, then you learn how to navigate. You're like, oh, it's not that bad. You have input values, data or statistics. The data would be related to actual data. Like you had a raw list of data. They said Tony collected times of students leaving school one fine spring day, and 45 students left, and these are the times it took for them to leave the school. Basically, if you didn't put your data in a list at any point, you don't have any data. There's no raw list of data. So we want to go to stats. So hit the right arrow and hit enter on the word stats. Once you do that, it's really quite magical. Because you look at what you wrote down on paper and what you need in the menu, and you realize, oh, it's like a perfect fit. Right? Because the mu sub O, and it's the same idea as the p sub O on the last, for the last hypothesis test. This is going to be the value. Oh, my arrow's going. How did that? I don't even know physically how that could be possible. We made a pitchfork or something. The value in your null and alternative hypothesis. X bar is X bar. SX is S. So 5.7, 2.1. 4,500 for some reason is still here. Well, not for some reason. It's I put in 4,500 for N in the last hypothesis test. My calculator thinks that every N is now 4,500. Right, well, okay, well, I'll have to change that. It's going to be 45. The last time I manipulated this, even in a different test completely, I selected the greater than. It held on to that also. All right, so you have to manipulate that as needed. But in the grand scheme of things, I'd say that's probably not an overly challenging thing to worry about. All right, so 5. That's what, 5 is what was in my null and alternative. 5.7, 2.1, 45, and then down to calculate. And you can run the numbers if you want right now, but I just wanted to take a sec and discuss very quickly the point behind all of this. Because, going in, I say it, I do the Batman reference and everything. It doesn't always land because it comes back to an idea that some folks just can't get out of their head, and I couldn't myself. It's like the mean time greater than 5.7. I look at it and say, well, yeah, the mean time's greater than, not greater than 5.7, greater than 5. I say, yeah, the mean time is greater than 5. It's 5.7. It says it right there. Why do I do all this crap? If my goal was to show that the average time to leave school was more than 5 minutes, didn't I just show that? But yes, but only for these 45 people. And if the idea is for us to use the information about these 45 people to draw a conclusion about everyone. All right, so these 45 people, they represent the light of the bat signal. The result of the hypothesis test is the bat signal. All right, so we want to know, is this true for everyone? Is there enough evidence from this sample to draw a conclusion about everyone? And all the stuff that we learned about involving probability allows us to transform from sample to population. All right, all of those probability skills allows us to do what we're doing here. All right. So calculate. I mean, when I was a student, I had to do a lot of this by hand. And as a teacher, I definitely did a lot of it by hand early on because I didn't know how to do it on the calculator. I think I told that story already. But now we have the ability to figure out these numbers without having to whip out like Z tables and T tables. It allows us to really think about why things are working the way they're working. So it gives us wiggle room. All right. So I have my p-value. I need to compare it with my alpha value. So again, I'll write the rule again. If your p-value is less than your alpha value, you will reject your null hypothesis. All right. If the p-value is less than the alpha value, you reject the null hypothesis. Okay. The p-value. Estimate is fine, but I'll go 3 significant. 0, 1, 5, 2. Alpha value is 0.01. Is that a true statement? No. Do not reject the null hypothesis. And this is where a little gray area comes into play here. Because depending on who you are, you might draw a complete opposite conclusion. I told you to use a 0.01 alpha value. But if I told you to use a 0.05 alpha value, then, well, 0.0152 is less than 0.05. You would then be able to reject the null hypothesis. So depending on the alpha value selected, you could actually draw the exact opposite conclusion. Right? So this is where you could kind of use statistics to, manipulate folks' thinking. All right? So in this case, though, the 0.01 was the value that we were instructed to use, for some sinister reason. Do not reject the null, so I keep the null, get rid of the alternative. So the null is true. The alternative is false. All right? The biggest, I think anyway, a bit of learning that can come out of this class related to this topic is just the idea to not take things at face value. Because in math, we tend to. Because it's usually a concrete answer. X equals this. Find this area, whatever. Here, there is gray area, but it's presented in a mathematical light. So when people say, well, I conducted a statistical analysis at the 0.01 significance level and I determined the outcome is meh, and you're like, oh, wow, that sounds fancy. I bet it's true. Well, no. The first question you should be asking is, well, why'd you choose 0.01? Now, if you had to, if you were kind of locked into 0.01, you didn't have a choice. It's a different story. But if you had a choice, why 0.01? All right. What I do is I run my entire statistical analysis first. I do all this work, and again, all this work. What I actually hand wrote here came from the problem. I technically didn't even have to write it. I needed the HO and the HA. I needed the p-value, and whether or not it caused the rejection. So all this work is subjective. But I did, under normal circumstances, if I were doing a project or something, I would do all the work first, come up with the p-value, decide what I want my conclusion to be, and then choose an alpha value that proves me right, because I like being right. Okay, so I would be like, all right, well, I got a 0.0152. Well, I want to be right because I think that it should be mu should be equal to 5. So I better not go with a 0.05 alpha value. I'll stick with a 0.01 because that proves me right. Anything else is going to prove me wrong. So that's where I'm going. And like, wow, how is that mathematical? Well, the mathematical part is coming up with the p-value. And in fact, what you should do, what everybody should do, statistically, what should be happening is that this alpha value stuff shouldn't even be there. That alpha value is to give people who don't have experience in statistics a benchmark for comparison. It's to give them a sense of, okay, well, this p-value, okay, well, what is it? How do I know what it means? Well, compare it to this number. If it's bigger than this, it's this. If it's less than that, it's that. All right? But really, the idea is, if the p-value is as close as it can be to 0, then that supports the null hypothesis. The further it is away from 0, the less support it has for the null hypothesis. That alpha value stuff doesn't really have much meaning, but in terms of actually getting a point across to have finality, it's used, but I don't think it's used correctly in a lot of cases, but also necessarily. Right? We do have to state the final conclusion. Oh, that was on the same page. Final conclusion in words, and again, follows the template here. But you can see this; it's a template. Templates are left as purposely vague, right? So it's not like you have to memorize a brand new one for this particular test. It's the same model. There is insufficient evidence to reject the claim that, and state the null hypothesis in words. The null hypothesis was mu equals 5. So that the population mean time to leave school. So don't just say the population mean. You got to tell me the population mean what? You know, what are we talking about? Time to leave school specifically is, that takes the place of the equal sign, 5 minutes at the 0.01 significance level. Now, the question was asking us whether or not it took longer for folks to leave school than that benchmark of 5 minutes. So, therefore, so the second sentence is required. Therefore, the claim that, so we want to state the alternative in words, and that was mu is greater than 5. So you could state, you know, we could write the population mean time to leave school is more than 5 minutes, but we've already established what mu represents in the context of this situation. So it's safe to say at this point that you could just kind of jump right to kind of a paraphrased version of it. All right? So therefore, the claim that the time is greater than or more than, I'll say greater than 5 minutes that's going to be false. All right. And that has more to do with the structure than anything else, because the second sentence is addressing the alternative hypothesis. The alternative, it turned out not to be true because we said that we're not rejecting the null hypothesis. We're not rejecting the null, which means we're keeping the null, making the null true, making everything else false. The everything else is your alternative. So first sentence true, second sentence false. The only one that's actually requiring a true-false definitive statement would be the second sentence stuff. Let's get that.